Swayam Prabha. Digital India. Educated India.
So, the agenda for today's lecture is polygon triangulation, but I think I should spend some more time on whatever we did a little bit on Voronoi diagrams in the last class, and sort of this would sort of prepare you up, set you up for the most important structures in computational geometry are these convex hulls or convex polytopes in higher dimensions, Voronoi diagrams in higher dimensions, and Delaunay triangulations, and the nice connection between them does set up a lot of things. So, to start with today, let us look into this Voronoi diagram computation of so the algorithm that we would discuss, rather we sort of did a small introduction to in the last class, was this fortunes plane sweep algorithm. So, the algorithm was the first algorithm for computing Voronoi diagram in R2 was a divide and conquer algorithm by Chamos way back, but it is kind of messy. Fortunes plane sweep, you have nice implementations. The other way of implementation is randomized, rather incremental kind of construction. You think of n points, you have inserted the first I points and you have constructed the Voronoi diagram till now. You take the I plus 1th point. Now, if you can quickly figure out where in which cell of the Voronoi diagram this I plus 1th point lies, then you know what are its close neighbors, right. And the new Voronoi diagram that will come up after the introduction of the I plus 1th point, you would appreciate that you would not disturb Voronoi cells that are very far off, right. They will only disturb locally, because Voronoi diagram works on close neighbors, fine. So, the idea of this incremental construction is you keep on inserting and you construct the Voronoi diagram, you take the I plus 1th point and then you insert. Now, to do this, what you have to do is, which I think I will discuss maybe tomorrow or day after. So, your algorithm would depend on figuring out in which Voronoi cell this I plus 1th point lies, right. So, say you have the Voronoi diagram with you. So, whatever it is, I mean my drawing may be wrong, but so you have some Voronoi diagram. And so, whatever it is. So, when the I plus 1th point comes, you have to quickly figure out which cell it lies, right. And then if you can figure out quickly that the cell that it lies in, because this is a partition, right. Voronoi subdivision partitions the planes into different closed and open convex regions. So, if you can quickly figure out which cell it disturbs, then you know that this some close neighbors of this are going to be disturbed. So, if I can reconstruct the Voronoi diagram only within this zone, then I will be done, because very far off Voronoi regions are not going to be affected. So, one can do a little bit of mathematics and show that on the average this disturbance zone is not going to be very much. There can be worst cases where you might take up like in your insertion sort, you might take up n squared time, but one can argue on this randomized incremental construction that I was talking of for your minimum detection, for your sorting, for your convex hull. So, you can also deduce something like that incremental construction for Voronoi diagram and Delaunay triangulation, right. But again that is worst case n square, but on the expectation it can run in n log n time. So, that implementation is also available widely. But let us come back and sort of discuss a little bit on Fortune's plane sweep that we left yesterday. So, let me pick up a nicely an example which would I think work for you. Let me have first a circle. Okay. So, these are the three. So, I try to draw a Voronoi diagram for you for so, these black points are this P1, P2 say P3, the points on which, and this violet colored point this. So, sometimes this which I can see possibly you cannot see. So, let me, so this violet colored point is the bottommost point of the circumcircle of these three black points, right. So, let me name them as maybe P1, P2, P3. So, these are your black points and this violet colored point is the bottommost point of the circumcircle of this tree, right. Now, what your sweep line did was, your sweep line was somewhere here. Think of the positioning of the sweep line which is just a little bit below P3, but above this violet colored point which let us call to be the circle event. So, let us call this to be the circle event. Okay. Now, this is the status of your sweep line. So, you have the three defining parabolas, right, okay. And so you know that your so you will have a parabola like this, then pardon my drawing, but I hope you can understand. So, now look into this fact that, so the parabola corresponding to the point P1 is this. Now, this part is hidden from the below by the parabola corresponding to P3. Okay. So, let me name this parabola as P1, this parabola as P3 and this parabola as P2. So, if you see from the bottom, right, what exactly do you see? You see this yellow colored or yellow ochre colored thing, right. This is what you see, the rest is hidden for you. Right, the rest part of the parabola is hidden for you. Understand? Now, look at the crossings of the parabolas. What they are tracing out for you? So, they are tracing out. So, this part of the edge, so this green part which was your part of the Voronoi diagram, which has already been seen by the sweep line and which is much above your. So, let me call this, as I did yesterday, let me call this to be my beach line, right. So, beach line is above your sweep line. So, above your beach line, this part of the Voronoi diagram has already been constructed, right. This part has also been constructed. Now, this intersection, can you see the colors? So, this intersection and this intersection, what is happening to them? As the parabolas sweep down, as the sweep line goes down, so the parabolas start coming down, right. So, your next intersection would be your P1 gets somewhere here, your P2 gets somewhere here, and then this is what is going to happen, right. No. So, this is going to stress this part of the edge, right, this remaining part of the edge, this is going to stress this, fine, and this one, right. Now, you understand? Okay. Now, see, when the sweep line touched P3, that is the situation I will call to be a site event, right. So, what did I say? How do you pick up a site event? You pick up it from a heap or a sorted list on the y coordinates, fine. It is better to handle it with a heap, fine. So, from the heap, first P2 comes, there is one parabola, then P1 comes, there is another parabola, then P3 comes, there is another parabola, right. First, this parabola is very slender. How do you figure out which part of the beach line it breaches? What you do is you store a left to right order of this beach line according to, like in this case it would be P1, P3, then again a part of P1, then P2, right. This is your left to right sequence of the beach line. This you can store as a kind of a balanced binary search tree, fine, but the index is the increasing x coordinates from left to right. The moment you get P3, look at its x coordinate and figure out, do a binary search, and then you can figure out which part of the parabola it is going to hit. It is a log n kind of operation, fine. Then you now know how this new beach line will behave. But the moment a site event comes and a new parabola appears and disturbs locally the beach line, what has happened is a new triplet has formed. Earlier it was just this P1, P2. Now there is a triplet like P1, P3, P2, fine. This can give rise to a Voronoi vertex. So, what I will do is, the moment this P3 comes, I will figure out from the beach line which is its left predecessor and right successor. So, in this case P3 is between P1 and P2. So, P1 is its left predecessor, P3 is its P1 is its left predecessor, P3 is its right successor. With these 3 points I will compute a circle, fine. Now, the center of the circle is going to be a contender for your Voronoi vertex, but you never know that there might soon come a point very close to P3 which might kill this circle, right. This can also happen, but this I till now do not know because this is still below my sweep line. So, what I will do is, I will look at this circle and insert its bottommost point into the same heap in which P1, P2, P3 was already stored. What is the priority? The priority is the y coordinate, right. So, in the heap I first arranged all the points in the point set P, this n points in a heap, I build the heap in linear time, and then I keep picking points from the heap, fine. So, these points will get picked up in their order of their decreasing y coordinates, fine, okay. And that simulates the sweep line. But I have to make the sweep line also go through these site events, because these site events will lead to the Voronoi vertices. But the point is, if you store as your site event the explicit Voronoi vertex or the center of this circle, then this might be above P3, no? Your sweep line has already passed it. So, the trick in here is, instead of the center, store the bottommost point of the circle, right. You can easily, given 3 points, you can compute the circle and figure out its lowest point. Insert that point, the priority being the y coordinate of that point, into the heap. So, sometime later when you pick from the heap, this point will come, and mind you, this circle has survived, the circle is not killed. So, then that means there is the chance of a, that is going to be a Voronoi vertex. But this could have been also a false alarm. In that case, this 3 triplet would be disturbed by some other new parabola. Then again you have to alter the beach line a little bit, throw away a false circle, insert a new circle, right. It is a little bit of a complicated algorithm, where you have to do a lot of bookkeepings, so that things really fall in place, but this is the essential idea. Now, if you look into it, what are your basic operations? Your basic operations are picking up things from a heap, inserting into a heap, searching in a balanced binary search tree to look at this x y order, this x order, right. So, there is this. So, what you do is, as Aritra must have told you, that when you store along sweep line a status, that is a, say, a balanced binary search tree, and the heap gives you the y order, right. All the operations that I do on these data structures are log n, right, searching predecessor, successor, then picking out the minimum from the heap, inserting into the heap, inserting into the balanced binary search tree, deleting from the balanced binary search tree, everything is a logarithmic operation. You have n points. So, that is why you have n log n. Bottommost point, yes. Yes. It might kill this circle. See, what you can do is store the bottommost point into the heap, but with that keep a satellite information that the center of this circle is this coordinate. So, you can always keep a satellite information with it, but the priority should be on the bottommost point and its y coordinate, so that the sweep line picks it up at a later point of time. Got it? So, this is kind of a very tricky, messy kind of algorithm, where you have to really do a lot of bookkeeping, but this is essentially the idea, fine. So, let us go forward. Now, I think I should mention one more thing. If you also look into this beach line and draw a line which is perpendicular to your x axis, that means you draw a line parallel to your y axis. So, draw any line which is perpendicular to the x axis, right. At how many points can these lines cut the parabola? Only at a single point, right. So, I will call this beach line to be x monotone, fine. I call it to be x monotone because if you take a line perpendicular to the x axis, it cuts the structure only once, but that is not true of if you cut it this way, na? There can be more than one cuttings, fine. So, this is a monotonicity is a property I will need later on also. No, the beach line is x monotone. It is always going to be x monotone, because the parabolas have the same directrix, no. Okay. There is the notion of which I will not discuss, this you might look up yourself. There is kind of this The Voronoi diagram that I talked of was the nearest neighbor Voronoi diagram, where you look at the collection of points q such that this is closer to pi than to any other pj. Now, what I say is for for a pi, look at the set of points q such that pi is the farthest from q. Okay. Now, think of the structure of that Voronoi diagram. It is interesting to think of the structure of that Voronoi diagram. If you have any point and you are looking for its farthest, na? So, does any structure come to your mind? Convex hull, no? Right? Because a point which is close by will not affect its structure. No? So, the points that are so earlier you were looking at close neighbor points, now you are looking at, right. So, this Voronoi diagram will have a nice structure, think over it. It kind of have a tree like structure, it will not have any closed faces. Anyway, let us move on. Okay. So, I would now sort of to give you this, sort of this is sort of going to set up what possibly Arijit will do after lunch today. He will give you nice connections, because with this, many of you are like fanatics of data science, machine learning, right. So, these are the buzzwords everyone hears these days, big data. So, essentially what happens there is you operate in very high dimensions. The data has huge dimension, and sometimes the dimension that you operate on becomes almost same as the number of points that you deal with, right. So, think of this, this is a 3-dimensional room and you are dealing with 3 points. Na? It is like geometry, the sense of geometry sort of changes. So, it makes sense these days to study high dimensional geometry and topology, and this convex hull, Voronoi diagram, Delaunay triangulation, these are kind of the most important structures in geometry that one studies at the very beginning. So, if you look at this this conflict structure based convex hull construction I was talking of in 2D. So, what was the idea? You had built a convex hull till now, and for each point outside, just first think of this sorting thing that I told you. What you are doing, for each interval created till now, you are maintaining a bidirectional pointer to the points that conflicted with this interval. So, each point knows the interval within which it lies, each interval also knows what are the points that lie within this interval. This is the basic philosophy. I took this idea, went to convex hull. What I did? I looked at the convex hull created till now, points which are inside are always going to be inside, forget about them, set them to null or whatever. Now, for each edge, I looked at the, so take a point inside, maybe the CG of the starting. So, first you had 3 points, constructed a triangle, take the CG. So, the CG will lie inside the triangle, right. Now, as you build up your convex hull, this point is always going to lie inside, fine. Now, what you do is that at each point of time, you take a point outside, join it with this point, right. So, this line did cut one of your convex hull edges. So, what you did was, for each point you know the edge of the convex hull it cuts, and for each edge you also know which are the points from which the lines cut this edge, right. This was the same conflict structure which I imported from the idea of sorting. Now, see, this simple idea even translates to higher dimensions. Think 3D, right. Arijit was telling you. So, when you had a 2D convex hull, you had only points and edges between them. So, 3D convex hull you will have faces which are kind of 2-dimensional facets. You have between faces you have edges, and these edges meet at vertices. So, you had 0-dimensional point, 1-dimensional line, 2-dimensional faces in 3D. So, in D dimension you will have this D -1 facet, D -2 facet coming down to 0 facet, which is a point. Okay. Now, what you can do is for each one of your facets, think 3D. For each one of your face, you know from a point outside that what are the faces that it cuts, what is the face that it cuts, linear structure, what is the face that it cuts to get into a point inside. And so, similarly for each face you know which are the points from which the lines goes through, right. So, the same idea works. Only this dimension will now start playing up. But you see that basic idea of randomized incremental construct, or let me talk it in terms of first incremental construction. What you can possibly do is start with a random permutation of this input point and then do this construction, fine. And again one could show that the disturbances on expectation is not going to be very much. So, what you did for points outside, you picked one point, right, and then you drew tangents in 2D. Here you have to draw sort of tangential spaces, right. So, if it is think, so you have to draw this kind of tangential faces, you figure out those faces, or first what you do, for this point you know the face that it conflicts to. From this point sort of build a tetrahedron kind of structure which has this face at the base and this vertex at the tip, fine. Now, this will create concave corners with its neighbors. So, keep killing these concave corners and keep growing face by face. Now, the point is in your 2D, when you are removing concave corners, you had to kill only one edge, right. But in here for a vertex you will have many faces incident to it. So, you have to tackle them, right, and that is where D comes into the play. So, D will get into the exponent. So, you will have something like n to the power of D kind of algorithm, right. So, that is the problem. Now, you see, now you think of this, if your D is of the order of n, then you are dealing with an exponential algorithm, right. So, this is kind of the curse of dimensionality for geometers. So, D is something with which geometers are bothered very much, but sometimes you really cannot escape it, because you have lower bounds where this dimensionality also plays up, right. Okay. So, let me do this lifting transform as I did yesterday. So, our idea was a point x y, let me do this math a little bit. A point x y goes to so my paraboloid is, let me name my paraboloid as z equals to x square plus y square. And the lemma that I try to prove is, let P Q R S belong to R 2. So, whatever I say is such that the convex hull of the point set would be centered at the origin, right. So, the origin lies within the convex hull, then the theory goes through, or else you have to translate and do a lot. So, let us make this assumption and let P naught, Q naught, R naught, S naught be their respective projections on L. first just look at this statement. So, I am saying that there are 4 points on the plane, and let this P naught, Q naught, R naught and S naught are their projections onto this unit paraboloid, that is hinged at the 0 0 of x y. And so, what I am trying to do is to show you an if and only if relation between S lying within the circumcircle of P Q R and S naught lying below the. So, now this, if you lift this P Q R onto the paraboloid, right, it is 3 points on the in R 3. So, there will be a plane going through it, fine. Now, my claim is if S lies within the circumcircle of P Q R, then this S naught. So, what is S naught then? S lifted onto the surface of the paraboloid, remember it, everything goes onto the surface of the paraboloid, right. So, this S naught is going to lie. So, you think of this paraboloid, right. So, here is somewhere your P naught, Q naught, R naught. So, there will be a plane passing through it. Now, what I say is S, if you lift above onto the paraboloid, it will lie below the plane passing through P naught, Q naught, R naught. So, the statement of the lemma is clear.